In this video, I will describe my development process and some technical details about the first assignment of Computer Graphics 2. Thankfully, we have been provided with a sample OpenGL program. It compiled out of the box on my system, and it handles all the basics of an OpenGL program so that we don't have to write any boilerplate code. I started by modifying the given sample code, and I removed the unessential components such as this parseObEdge function, because all the geometry in this project will be generated in runtime. I also removed these struct definitions in favor of the definitions given in GLM library, because this library provides matrix operations, therefore it's more convenient to use. I used the definition of Bezier surface given in this slide. At first, I considered using the shorter definition given in the next slide, but it turns out that it's easier to implement this one because the matrix operations are already defined by the GLM library. One minor problem I ran into while implementing this is that the GLM library stores the matrices in column-wise ordering. So if you write the matrix as you see here into an float array and give that to make matrix function, you will actually get the transpose of that matrix because of the column-wise ordering. Naturally, you will need to take the transpose of this matrix to get the original one. But this is not a big deal since we need both the matrix itself and its transpose in the formula. For the tessellation process, I followed the guidance of the slides again. As shown here, I sampled vertices in a grid and formed triangles among them. I used counterclockwise winding order because that's the default way to describe the front faces in OpenGL. In VS Codium, I created some launch configurations to compile the program and run it in debug mode automatically, so that it's easier to catch the bugs early. At this stage, I am able to create a Bezier surface and render it without the normals. The Vim emulation of VS Codium is sometimes weird. I used the approach presented in this slide to compute the normal vectors. It basically takes the derivative of the surface with respect to two parameters and takes their cross product to find the normal vector. In the formulation, I tried to reuse the common terms as much as possible to avoid redundant matrix multiplications. Moreover, due to the positioning of my camera, the surface normals were not pointing towards the right direction, they were pointing away from the camera. To solve this problem, I changed the ordering of the operands in the cross-product formula. At the current stage, the program is able to render the Bezier surface correctly with the normals, and we can change the shader program with J and enable or disable the wireframe mode with K. For reading images, I used the header-only library called stpimage as recommended in the homework document. After that, I enabled another vertex attribute array and used SNT parameters as UV texture coordinates. However, while implementing that, I forgot to specify the vertex attribute pointer properly. Because of that, my whole system crashed during the process. For shader, I sampled the texture color and used that as diffuse reflectance coefficient so that it's affected by the lighting properly. Currently, the program is able to render the flag with texture, and I also added keyboard shortcuts to change the number of samples. I implemented the surface normal computation previously, but if you actually decrease the number of samples enough, you will see that at the current stage, the program is able to render the Bezier surface correctly with the normals. Let's just say it doesn't work properly. This was actually given in the assignment document, but I skipped that part while reading it. The normals need to be computed from the sampled mesh, not the underlying surface. The normals are computed by averaging the normals of the neighboring triangles. However, the contribution of each triangle should not be the same. Otherwise, we get artifacts like this one. For example, in this case, the bottom triangle should weigh about 2 times more than the triangles on the right. We could compute this more carefully using the angles, but using this rule of thumb was enough in this project. In this blog post, I explained all the details about the animation implementation in my project, so I will not repeat myself here. To complement the blog post, I will talk briefly about how I implemented the normal maps. Do you wonder why your textures look like printed images slapped on top of cardboard boxes? That's because you are not using normal maps. We define the base geometry of an object using vertices and triangles, but the small imperfections on the surface of an object will affect its lighting as well. Normal maps attempt to emulate this by encoding the surface normals of a texture into an RGB image. In the shader, these colors are converted into normal vectors and used in lighting computations. Normal maps allow us to easily increase the realism significantly with negligible performance penalty. For example, this is a flag without the normal map. And this is the same flag with the normal map. The sample and patch counts are the same, so all that illusion of detail is given by the normal map.